So, for our cross-sections project, my group and I, which consists of me, Austin Krigbaum, and Joshua Mallon, used this baby, which is f of x equals 3 minus the absolute value of x minus 3. And as you can see by the graph, it's just an absolute value function reflected over the x-axis and then shifted up 3 units and right 3 units. And it's pretty cool, if I do say so myself. Now, for my part of the project, I used the triangular cross-sections, equilateral triangular cross-sections. And we also used the midpoints. So as you can see, it's pretty cool, which it is also an underestimate of the actual theoretical volume. So yeah, for our calculations, to calculate the area of the cross-section, which is a triangle, an equilateral triangle, as I said, it is root 3 over 4 times the length squared, which it's, yeah. So, in order to find the volume of each individual slice, essentially, since we used each width of each slice is 1 unit, you just have to plug in that value for h, and you get it. You get the volume. So basically, for the first slice, which is 0.5, the length is 0.5, as I said. And so yeah. So when you do that, you take 0.5, you square it, and you multiply it times root 3 over 4. And when you get that, you get root 3 over 8, which is equivalent to about 0.10825 units squared. And in order to find the volume of each slice, you multiply that times 1, so you get the same thing, 0.10825. So yeah. In order to find the volume of the second one, you plug in 1.5 and you square that, and then you multiply it times root 3 over 4. So you get 2.25 times root 3 over 4, which is equivalent to about 0.97428 units squared. And in order to find the volume, you multiply it times 1, which, yeah, I know. It's really difficult. So when you do that, you get the same number, 0.97. So then, for the next slice, the largest slice, so you take 2.5 and you square that and multiply it times root 3 over 4 to get 6.25 root 3 over 4, which, when you actually plug it into a calculator, gets you 2.70633 units squared. And in order to get the volume, you multiply it times 1, and that times 1 is the same thing, which is 2.70633 units cubed. To find the approximate volume of this, which is the model, essentially, using Riemann sum, you go ahead and take all those numbers we just had, add them together, and multiply them times 2, because this is an even function, reflected across the line x equals 3, which, yeah, pretty nifty, I know. So you take all those, add them together, and you get 8.75. Multiply those times 2, you get 17.5. Then you multiply that times root 3 over 4, and you get 7.57772 units cubed. Now, in order to find the theoretical volume, which is assuming each cross-section is a triangle, you go ahead and take the integral from 0 to 3, multiply it times 2 times root 3 over 4, or root 3 over 2, because the 2 and the 4, they cancel out. So, when you take that from 0 to 3, go ahead and plug in the function. It becomes 3 minus x quantity squared, which is just x squared. What? If you take integral of that, you get x cubed over 3 from 3 to 0. You get 27 over 3 minus 0. You get 9 times root 3 over 2, which is about 7.79423 units. And as you can tell by that, it's bigger than the approximate. So that means the approximate is an underestimate. Alright, I'm throwing it to you, Josh.
Thanks, Ryan. So my cross-section was the square, and to find the area of each slice, you do length times width. So, in my case, and for a square, it's just x squared. So for the instance of the small one, it's 0.5 times 0.5, which is 0.25, and then the length of each one is 1 unit, so it's just 0.25 units cubed. For the medium one, it is the same concept. It is 1.5 by 1.5, which, when multiplied together, it's 2.25. And so for the large slice, it is just 2.25 times 2.25 times 1, since that's the length. So it's a 6.25 units cubed. So for the approximate value of this model, I did the Riemann sum. So 2 times 0.5 squared plus 1.5 squared plus 2.5 squared. So you're going to get 17.5 units cubed. And so for the theoretical volume, it's 2 times the integral from 0 to 3 of 3 minus x quantity squared dx, which is 2 times the integral of 0 to 3 of just x squared dx, which, when you do the integral of that, it's 18 units cubed. And that's pretty similar to our approximate value, which was 17.5 units cubed. So that tells us that the approximate value was a underestimate.
Thanks, Josh. Now let's go to Austin.
Hey, for my section of this project, I had semicircles for my cross-sections, so the area is equivalent to pi over 8 times the diameter squared. Diameter in this case would be the y value for our function at each x value point, which means for our y values we're going to have 0.5, 1.5, and 2.5. We have two sets of those because our function's even. So for this, it means that our smallest two slices, which are the two on the ends, will have an area of approximately 0.098175. And our two medium-sized slices, which are going to be in between the two the small and the large, obviously, are going to be approximately 0.88357. Our two largest slices in the middle will both be approximately 2.45436. And the volume for each of these, since our depth is only 1 unit, would be 1 times the area for each of them, which is going to be equivalent to the area. Now, the approximation for the volume of the entire function is equivalent to all those added up, which are Riemann sum, which for us was at a midpoint Riemann sum, which came to be about approximately 6.872234 for the semicircles, and the theoretical, or more correct, rather, volume came out to be approximately, or equal to, 9 pi over 4, approximately 7.06858 units. Thank you, and that has been the project.